All right, welcome. So in this video, I want to start talking about an artificial neuron, which is the core component of artificial neural networks. So last video, we talked about neurons and brains, and neurons had a bunch of functional components, and they were connected together in different specialized regions of the brains, things like this. But for computer scientists, when we want to harness the power of neurons and neural nets, we start by abstracting away a lot of those real-world details. And what we see when we look at a brain is we see a network or a graph of nodes, specifically neurons, that are connected to one another. And that's, for our purposes, a graph. And so what we want to do is we want to build our own graph-like structure that in some ways mimics the behavior or performance of the brain as it is a network of neurons. And to do that, we need to have the central unit, the main unit, the neuron itself. So we're going to take a look at what an artificial neuron is. There are a few different kinds of artificial neurons. We're going to look at a very common variant of the artificial neuron that is present in many artificial neural networks. So what we're going to look at today is sort of a standard definition of an artificial neuron. Now, what a neuron is going to do for us is, in a very abstract sense, a biological neuron takes some inputs in and decides whether it wants to send an input out, depending on the inputs that it received. And we're just going to create a little structure, a little gate, if you will, or a little computer that does the same kind of thing. It's going to take some inputs in, and then it's going to make a decision about whether it should send an output out at the end. So I've got a little diagram here. So the sort of light blue area here, that's going to be the neuron itself. We've got some inputs coming in on the left. We've got some outputs going on the right. And we've got some details here about what an input or an output might be for an artificial neuron. So it says here that inputs and the output could be binary valued, integer valued, or real valued. What we are saying here is that the value that these inputs or output might take could just be a binary value. So it might just be zeros and ones. We might be putting zeros and ones in for all of our inputs here, and we might be expecting coming out on the other end another 0 or 1. In that case, we could really think of this as some kind of logic gate. That's how logic gates work, for instance. Neurons don't have to work in that strictly binary space. So we might also decide to expand that. Sometimes we might want to have a negative value in there as well. So we might have plus ones, zeros, but also negative ones potentially as our inputs or outputs. So maybe all of, there's nothing telling us that all of our inputs have to be of one kind and so on. So we might have inputs that are 0, 1, but maybe our output is -1, 0, or 1, something like that. So we definitely can switch it up like that. Now, binary valued are common for maybe explanations and demonstrations on how neurons work. We're probably going to do that a little bit later on. Integer valued, not super common, but the most common working in the regular neural nets that you might find are real valued neurons, meaning the inputs are real numbers and the outputs are real numbers as well. And often they're restricted in a range. So for instance, a very common range to restrict it to might be 0, 1. So at the minimum we have 0, at the maximum we have 1, but we could also have inputs or outputs that are in that range as well. It's not strictly restricted to those two values. And then likewise, we sometimes want to expand that to -1 as well, so that we have negative values as well. And nothing specific tells us that we need to cap these values at 1. It could be -2 and 2. That really depends on what are you using these neurons for, what is the neural network that you're creating used for. But because we can normalize things a lot of times, 1 is a very common one to pick. We can just normalize if we want something bigger or smaller afterwards or during the computation. And one of the reasons why we are a little bit, we don't worry as much about whether we should bound those values at 1 or 2 or 7 is that we have weights involved as well. So when these inputs are actually input into the neuron, they are multiplied by their weights. And so those weights can act as those scalars if we need to. If we needed that input to be twice as big or half as big, the weight that we assign here could take care of that for us. So normalizing all of our inputs and keeping them in a range 0 to 1 makes sense if we're going to already be modifying them after the fact with these weights that can range. So it's also stated here, well, what are these weights? The weights are real valued as well. This is more common, even in binary valued networks, integer valued networks where the inputs and outputs might be binary valued and restricted. Our weights are still very commonly real valued. So in the middle, in the processing, things all get turned into real values, even if afterwards we put them back into binary valued or some other form. The other thing here is our weights themselves might be bounded or unbounded. So I gave reason why we might bound the values for our inputs and outputs within a range 0, 1, because 1, it's convenient, and 2, we can do that knowing that there are these weights at play later on. But if we then choose to bound the weights as well, now we are restricting the kinds of values that might be able to go in or out of our neuron, and that might affect its behavior in a way that we don't want. So we want to be, we do want to think about that. It's more common to just have unbounded weights, so allow our weights to range in any range we want, all the way up to, the maximum integer, effectively that, or the maximum real number that we can express in our machine, and down to the minimum if we need to. But commonly in neural nets, even if you do have unbounded weights, it's very common that those weights are bounded by the performance of the neural network, meaning that whatever learning algorithm or whatever tool you're using to adjust these weights, just by the nature of the learning algorithm, will probably keep them in a nice restricted range for you. So this choice, as I said, maybe keeping them bounded could have an impact. This choice is one that, often we might just leave them unbounded unless we have a good reason to end up bounding the weights. All right, so this is just the general structure of the neuron. You may have noticed that one of our inputs here looked a little bit special. So when I separated them off here, I kind of made this one special, and I've actually changed its value now. We might refer to the input coming in here as x0. That's very common. But in this case, the first input is very commonly called the bias input, and it is always set to 1. The bias input is always set to 1. It's not always the first one. It can sometimes be the last one, or it just might be separated specially as a different one, different from the input altogether, just called the bias or something like this. The purpose of the bias in a neuron is to ensure that the neuron has some ability to fire, and remember that is send a signal on along to other neurons in the future. It should have the ability to send that signal even when the signals it's getting on its inputs are all zeros. So if we imagine they're all zeros, so you're getting no input coming in, even when you multiply zeros by a weight, they're still zeros, so it's all zeros, but maybe we still want our neuron to be able to fire off a message in that case. Well, we set one input that is always set to 1. And we have a weight assigned to it as well, and this is our bias input. So if we need that on so that we can send that signal, we have some signal coming in that we can pass along. And then if we don't need this, we can just always set our weight to 0. So we can always set our weight to 0. And also, if we want our bias to be different than just 1, maybe -1, we can change our weight to be -1, and now we have a negative bias in there as well. So we usually have one input for our neurons called the bias input, always set to 1, that allows us to kind of program in a default performance for our neuron, given that it might get no input at all. Now, I hinted at this already, but when the inputs come in are read, they are then multiplied by the weights, and then they are summed together. So, and we can see this over here in our diagram, and the label for our neuron here has this sum, where we sum over all the inputs and we multiply them by their weight. So we have the weight multiplied by the input, add them all together, and then we're going to put them through this function. This function is called the activation function for our neuron. So it determines whether and what output we give. Okay, we call this the activation function. And I'm being a little bit agnostic about this activation function right now. I've just called it F because there are a variety of different activation functions we might use in our neuron to get different kinds of behavior for our neurons and our neural net. For instance, here's an example of an activation function, a very simple one called a step function. This is very commonly used in binary valued neurons where we have binary inputs and binary outputs. We'll use something like this in a future example. This particular step function, you can see, has the value 0 until it gets to 1, and then it bumps up and it becomes 1 after that. And so I've got a sort of just the functional definition down below there. It's going to be 0 if x is less than or equal to 1, and it's going to be 1 if x is greater than 1. So we could use this as a function in there that determines we add up all those values. Remember, we multiply. We have this weighted sum of xi times wi, multiply them all together, add them all up. If that value now is greater than 1, we will send a 1 out. If otherwise, if it's less than or equal to 1, we send no signal out. And that's maybe just how this particular neuron might work. Now, step functions are common, as I've said, maybe in a binary valued, but like I said, real valued is more common. Real valued neurons are the more common types of neurons, meaning our inputs and our outputs are going to be real numbers. And so for that reason, we need to have a function that's maybe a little more sophisticated, that's going to output a whole range of real numbers. And to do that, we use a class of functions, or at least one of the types of activation function that are very popular and common are called sigmoid functions. And this particular sigmoid function that we use here is called the logistic function. It is a function that's related to the growth of populations in a biological sense. And so we're sort of borrowing this function from those other sciences. Why? Because it has a nice behavior for us. What is it? What is this behavior that we like? Well, it's sigmoid, and that's just sort of a fancy term for S-shaped. You can kind of see it's a little S-shaped, this one here. This is an S that's been really stretched out, and we're going to show how we can squish it in a little bit here in a second. But that's what sigmoid means, is S-shaped. And the reason we want this is if our inputs are, say, really, really high, this sum of our weighted inputs is really high, then we probably just want our output to be 1. And if our sum of all these weighted inputs is really low, a really small number, or really big negative number, then we probably want our output just to be 0, say, in this case, assuming our output we want to range from 0 to 1. And somewhere in the middle there, we probably want it to transition from 0 to 1. And where in the middle we want it to transition, well, that probably depends a lot on what we're using this neuron for. And for this purpose, for this example, I've just put it at 0.0. You can see that at 0.0 here, it is actually at exactly 0.5, the value of this function. And so that's kind of the crossover point where we might say that it crosses over from not firing when it's below that to firing when it's above that. Now, of course, the way the neuron actually works when it uses one of these functions is if its sum of weighted inputs was exactly 0, then this function would output exactly 0.5. And one of the things we like about these S-shaped functions and sigmoid functions is that usually they don't spend as much time in the region where they're ranging from 0 to 1. They spend most of the function is spent either at one of the extremes, either at 0 or at 1. Now again, this particular example of the function doesn't show that very well because I've just captured this function from -2 up to 2. So I've only got the function here considered when this sum is between the range -2 or 2 roughly. Now if I zoomed out a lot, say maybe from -200 to 200, then what we would see is this whole curvy bit that looks really stretched out will instead look really, really squished. And we will get a very fat, what looks like a very quick movement from 0 to 1 as we cross over the 0 line. So think for the moment just that we've got kind of a zoomed in perspective of this one. And again, in a second, I'll give us a couple more examples. Before I do that, I want to look, so why did I pick this one first? What is it about this one that is worth looking at first? is all of the constants that we could add into this function are set to something simple like 1 or 0. So this is how I kind of remember the function when I need to. Of course, you can look this up. Again, I mentioned it's called a logistic function. And so this function here, we have a 1 on the top divided by this kind of weird fancy business where we have 1 plus e. Remember, e is Euler's number, which is 2.78 something like that, and it is the base of the natural logarithm, which is used in calculus a lot. So that's what that e is here, and we're taking that value e and we're raising it to the power of minus x. And remember, minus just means a fraction, so technically we have 1 over e to the x here, which we could write, it's just a little nicer to write it with the negative exponent here. And if we plot this function, which is exactly what I've done here, we get this graph. Okay, we get this sigmoid function. We can also see, if we zoom out really far, that the minimum value that this is ever going to take is 0, and it actually has got an asymptote that it approaches as we go to negative infinity, and then vice versa. As we go to positive infinity, this will also approach the asymptote of 1, meaning it keeps that neuron signal right in that range that we were hoping for, maybe between 0 and 1, if that's what our design document told us, is we should keep these neurons between 0 and 1, then this function does a good job, no matter how big x is. And I want to point out here, x is standing in for this big old sum right now, okay? So we take that big old sum, assign it to x, and then compute this function, and that's going to be our output y, all right? So no matter how big this sum is, we're never going to get higher than 1. No matter how small it is in the negatives, it's never going to get below 0. So that's why we like this function. Now, since this is the first version of the function where I said, everything's kind of set nicely to 1s and 0s, what happens if we come back and we say, yeah, but wait, this function is too stretched out for me. I want it more squished. I want it to look more squished. Maybe the ranges of inputs, maybe the sum that I'm expecting is going to be between -1 and 1 most of the time, in which case this is not a very good function at all. This is actually a pretty bad function. And in some of the neural nets that I've used in my experiments, this is exactly turned up for us. We've been wondering, why is the neural net not working very well? And then we look and we say, oh, we're stuck in this not very good region of the function, so we made some changes. So what change are we going to make? Well, we're going to start by adding in a coefficient for our value x. So what I'm going to do here is I'm going to change that from -x to -4x. And again, I've done this kind of deliberately because, as I mentioned in this experiment where we were having some problems, we had to fix the problem, and we wanted it to, when it was close to -1, hit 0, and when it was close to 1, hit 1. And so we just plotted a couple different graphs and went and found one that we thought was going to work well for us. And in this case, we picked 4x. So that's where I got that from. You can see that by increasing the coefficient of x here, we can make this slope more vertical. But if we make this coefficient here, the 4, if we reduce it, we can make that slope more stretched out, more horizontal. And so we sometimes call this parameter k, and we can range k to control the shape of this s. And again, we can do what I'm doing right now, and what I've done in the past is I can deliberately select a value that I think is going to work well for my neurons. That's very common. Or I might also use some kind of procedure to learn this value so that I can adapt it to be good for whatever performance I'm trying to use it for. So now what I've done is I've made another little change where I've added a -1 inside. I've now added brackets there too, but I've put instead of x, I'm doing x -1 instead. And we can imagine doing x + 1 or whatever it is. Effectively, what we're thinking of doing here is we're taking this whole sum, and after we've computed the whole sum, we do -1 again. Okay, we do 1 - 1. That's what's happening here. And what that does is allows us to shift the middle point of our sigmoid function, where it passes through the 0.5 point specifically. we can shift to a specific point. And like we have with other binomials and so on, we have to shift it in the opposite direction. So we need to do -1 down here to get us to shift it up to +1 over here, or vice versa. And I've only shifted it 1 here because otherwise my graph would have moved too far away and it wouldn't be easy to see the effect of it. But we can shift it, of course, in any direction by any amount that we want. If we wanted that center point to be at 100, we could just do -100. We also commonly give this parameter a name. We often call it m. And we can now see that we can change both the slopiness of the graph and then its center point here by modifying now m. So we have k and m, two different parameters we can use to modify this function to get different shapes. Now here's a final version. This is another one that I've used a lot, and this is one where I've now decided, hey, maybe my neuron needs to output -1s and +1 in a range rather from -1 up to +1. And to do that, I needed to change two things. I needed to change how big of a range vertically this function goes to. For the last couple versions or examples, the range was always 1, from 0 to 1. But now I need it to be 2, from -1 up to 1. And so the first change I make here is by changing this parameter up on top, which is was set to 1 before. I've changed it to 2. We sometimes call this one L, and this is going to tell us what the maximum value that we range up to will be. So if I didn't add the -1 on here, we would have the same graph going from 0 up to 2 instead. So change this up to 50 and we got 0 up to 50 instead. Now I also wanted it to not start at 0, I wanted it to start at -1, and so that's where the -1 comes in here. We shifted it down by doing a -1. Okay, so I first changed this parameter to get it to a 2, and then I shifted it down by 1. Now, this parameter is usually called L because it actually is a parameter of the logistic function, but the -1 is not considered to be part of the logistic function, and so it's not usually given a name, although we could give it a name if we want, O or P or something like that, and then we would have 4 parameters that we could vary in this logistic function to move this shape around, move it up and down, move it left and right, and change the slopiness of the shape. And that's usually with that many degrees of freedom, we can make all kinds of interesting sigmoid functions that we might like. Now, with that said, sigmoid functions and this particular version of the sigmoid function aren't the only kinds of activation functions that we could use. There are other activation functions, sigmoid activation functions that we can use, for instance, for this exact purpose, going from -1 to 1 if we didn't want to use this one. And then there are other activation functions that are not sigmoid at all in their shape. Okay, well, we could get another sigmoid function that sort of flips this along the if we flip it over a horizontal mirror here, so we go from 1 down to 0. That's something that we could do as well. But we can also make shapes that maybe peak at a particular value and kind of have more of a normal distribution. So there are a lot of different kinds of activation functions that we might use, given that we might want our neurons to do different kinds of things. All right, let's talk a little bit about what neurons can do now. So artificial neurons, I've kind of been hinting that these things maybe look like little gates. Maybe they're kind of like logic gates. So can they actually perform the behavior of a logic gate, or some of the simple ones that we might expect? And so the simplest one that we can start with is the NOT gate, which only has one input. Now, of course, for our artificial neurons, we're always going to have, n+1 inputs to include the bias input as well. And so for this particular example, we actually need the bias input to make this work. And I'm going to show you why. This one's actually a little bit clever. Now, why we need the bias input is because, remember, the way NOT works is if our input is 0, we want the output to be 1. And this is exactly the case that I was talking about why we need a bias input, which is if all of our inputs are 0, meaning no signal is coming in the power sense, you could think of this as literally being there's no actual electricity or energy coming in. And if there's no actual electricity or energy coming in, there can be no electricity or energy coming out. And so this is why we might imagine having this bias input. We could think of this as actually plugging it into the wall or something like that, where we always have energy coming in on this signal, so that if we need to send a signal out, we have something that's going to trigger this for us or allow us to do this. So what that means is, in this example where we're going to implement the NOT gate, I've actually set the weight for my bias to also be 1. I've said in the past that if I didn't want to use that bias for whatever reason, I could just set it to 0. That's fine. And then I'm kind of just ignoring it or treating this as though it's not there at all. But in this case, I'm turning it on. I want it on. So what that means is, let's just think for a second. We're going to imagine our correctness. It doesn't really matter what weight we have here, but as you can see, it's set to -1. That if we set this up, we're going to have 1 times 1 here. That's this first bit here. And then if our x1 is assumed to be 0 in this first case, we're going to get its weight, in this case -1, multiplied by 0. But since it's multiplied by 0, no matter what weight we had there, we're getting 0 here. So we get 1 times 1 is 1, plus 0 is 1. And in this particular neuron, I've gone ahead and set my threshold to be 0.5, meaning if the sum that we compute is greater than this threshold for our step function, it's going to output a 1. So in this particular case, 1 is greater than 0.5, and so our output is going to be 1. Okay, so again, how this is going to work is we're going to take all our inputs, multiply them by our weights, and then compare them to this threshold to determine what our output is. And what we've just done is confirmed that when we put an input of 0 in, we get an output of 1. So we could put a little check mark here and say, first case done. The second case is when we get a 1 here. And that's why this -1 is going to be very important, because remember, when we set up our bias, the default performance of this neuron, if it's getting no input, is to fire off, to say 1. But now that it's getting input, now that it's getting a 1 in, we don't want it to fire off a 1 anymore, which means we need to cancel out the default input somehow. We need to take this 1 that's going in there and get rid of it. And so the way I'm going to do that is putting a negative weight in here. The negative weight is going to take that 1, our input here, so if x1 is equal to 1, we get that input, and we multiply it by -1, this weight, we now get -1. That will cancel out with our +1, that gives us 0. And now when we compare to our threshold of 0.5, we see we're less than, and so we output 0. So again, just confirm one last time. If we put a 0 in on this neuron, we get a 1 out. If we put a 1 in on this neuron, we get a 0 out. So this neuron, as designed, implements a NOT gate. Okay, so our simple neuron is capable of doing NOTs. What else can it do? Can it do an AND gate? So let's try. So let's see what we're going to do here. Now, for the AND gate and the OR gate that we're going to look at next, we don't need that bias anymore. We might need it if we were going to do maybe a NAND gate or a NOR gate or something like that, where we've got that NOT part in there again, right? But in this case, there's no NOT, it's just a simple AND. So we actually are going to just set that one to 0. So I could delete it out, but I just want to show that for this particular case, yes, we still have a bias, but I've set the weight to 0 so we can ignore it. And instead, what I'm trying to think is, well, what is the input going to be? If both of these are 1, if both of them are 1, we want to output a 1, but otherwise we don't. So I started by just maybe guessing, well, okay, let's just put weights of 1 in first and see what would happen. If we put weights of 1 in, and we had 1 and 1, both our inputs were 1, we would get 1 and 1, 1 plus 1 is 2. So I went ahead and I decided, well, maybe I should put my step function, the threshold, to be at 1.5. That way, if 1 plus 1 is 2, 2 is greater than 1.5, we'll get the expected output. What we'll also be able to see there is that if we don't have two 1s here, so that we can add up to 2, that if only one of them are on and the other one is a 0, then we would have a sum of 1. And 1 is less than 1.5, and so we would get an output of 0. And again, I've confirmed this here. You can go and verify with me. If both are zeros, the total sum of our input is going to be 0, so we output 0. If one of them is 1 and the other one is 0, the total sum will be 1. And again, less than 1.5, our output will be 0. And for the other case where the other one is 1, and then only when both are 1 do we have a sum that adds up to 2 that can exceed our threshold and output 1. So this is simpler, if you ask me, than the NOT gate in terms of design or understanding it. We just sort of let the inputs come in as normal, 1s or 0s, and then we just kind of count. We use the threshold to count them. If there's at least 1.5 of them, that means there's 2, given that these are binary valued. And we know that that's the AND should be output as a 1 now, and otherwise we will output a 0. So before I maybe show it, if you want, I might say, well, pause for a second and try and do an OR gate, because we've got a very simple setup here that can be modified quite easily to turn it into an OR gate. So all we really need to do to turn it into an OR gate is change our threshold. In our last one, in the AND gate, we had a threshold of 1.5 because we wanted it to be triggered only when both of them were set to 1. But now we want it to be triggered if either of them are set to 1, including both. And in that case, we'll just lower the threshold. So now remember, in those two cases when only one of them were set to 1, for instance, like in this case, we are going to have a sum that's equal to 1. And we want that to exceed our threshold. So we bring our threshold down to 0.5 to make sure this is now a greater than, so that we output a 1. Again, in our other case, we also, it just happens to be a different input that allows us to get to the sum of 1 again. And the AND case that we were considering before is still a sum of 2. And of course, that's going to exceed our threshold of 0.5. So sure enough, we can do an OR gate. Now, the last thing I want to look at in this video is, well, if these are the kinds of gates that a artificial neuron can do, what kinds of gates, or what kinds of logical operations maybe, can it not do, if any? And sort of famously, there is one, there's more than one, but one in particular that is famous for not being able to be computed by a single neuron, and that's the XOR gate. And I'm just going to show an example of why that is here for a second, by trying to build one hypothetically that will solve an XOR gate. So I'm going to consider, to start out, any bias and input weights. So say we have W0, our bias weight, W1 and W2 are two input weights. Okay, and again, for the moment, I'm going to say consider any ones you want. I'm going to have a little diagram that's going to help us see what it is, but then what we're going to try and do is see if we can find a threshold. So sort of like we just did in our last example where we said, hey, let's move that threshold down so that it's in the right spot to give us the OR gate instead of the AND gate. We're going to do the same thing here. We're going to consider a threshold, and we're going to maybe move it if we need to, or try and find a place that we can put it so that it's going to give us the output that we want. So I'm going to start with the simple case. I'm going to go through all 4 of our cases, and each case is going to result in some kind of condition on our threshold that we're going to try and uphold. So I'll just give you an example to start here. Case 1, if both of our inputs are 0, okay, then what are we going to get? Well, we're going to get our bias weight times 1, so that one we know is always on, and then these two are multiplied by 0, so they get canceled out. So when we actually simplify that, we just get W0. Now, what we're computing here, this is the value of the sum, the weighted sum after our inputs come in. It's W0. And what we need to determine, we're trying to pick a threshold, and so we want to know, in this case, 0, 0, what are we supposed to output? Well, for exclusive OR 0, 0, if they're both 0, we're supposed to output 0. So in this case, the neuron is supposed to answer 0. So now what that means for us, for our threshold, if we want our threshold to, or if we want our neuron to answer 0, our threshold must be greater than whatever this weighted sum is going to be. And since we computed it to be W0, we've got this nice easy condition here. Our threshold has to at least be bigger than W0. Okay. Now at this point, I need to point out that W0 could be anything. We haven't said anything. It could be positive or negative. And so I've actually put a W0 on a number line here to show you that, let's just assume this is where W0 is. Again, if you want positive or negative or 0, you could make it 0 if you want. All we know is that our threshold needs to be greater than that. So at the moment, I've kind of made a dotted red line here tentatively. This is where I could imagine drawing my threshold right now. Now, the other three cases are going to create other conditions for us. So let's look at the next one. So in case 2, we're going to say that we have x1 is going to be 0, and then our x2 is maybe going to be an input of 1 now. Again, we can compute our weighted sum. What would our weighted sum be now? Well, now it's still the bias bit, the W0, plus the input that's coming in, so W2. So now we have W0 plus W2. And we go and we look at our input and think about XOR, and we think, okay, 0, 1. What is the right output for 0, 1 for XOR? That is 1. Okay, and so again, using the XOR as a guide, we're saying, okay, so the neuron in this case should answer 1. And to do that, that means our threshold needs to be less than the weighted sum. The weighted sum needs to exceed the threshold now so that we can output 1. So we get another condition, a little bit more complicated, but still pretty simple. Our threshold needs to be less than both of these added together. So again, I've just kind of arbitrarily put this here. So this difference here would be W2 then, okay? And if we leave our threshold where it is greater than W0 and less than W0 plus W2. So right now, this is a checkmark threshold. It's satisfying both of the conditions. If we draw our threshold here, we can answer 0 on this one like we want and answer 1 on this one like we want. So far, so good. To make this true, our W2 had to be positive. We had to put it on this side of W0 for this to be a 1 and this to be a 0. If we made it negative, it would have showed up on the other side of W0. And no matter where we drew a line, then we could still draw the line between them, but now we would get the wrong answers. This one would get 1 and the other one would get 0 when we wanted it vice versa. So we needed our W2 to be positive here to get this to work. Otherwise, we were already screwed up by this case. So far we're getting cornered a little bit, is I guess what I'm getting at. We've made one force move. We have to make that positive. So let's go ahead and do the next one. So now we're on case 3. What have we done? We switched which one is 1. So x1 is 1 now, x2 is 0. Again, when we sum them together, we get our bias term, and again we get this extra term. It's just not W2 this time, it's W1. Same condition though for our XOR gate. It's still in the 1 condition. We still have 1 correct, or 1 on and 1 off, meaning we should be answering a 1. So our neuron should answer 1. So again, that imposes our threshold must be less than this sum. Less than this sum. So I've gone ahead and put another arbitrary point here. In this case, I assumed W1 was bigger than W2, but that didn't have to be true. We could just swap these two labels and it would still be true. Okay, I haven't written any numbers in here, so this is very general and arbitrary. Okay, this could be a really big gap like 1,000,000, or it could be really small like 0.0001. I haven't written any numbers, so it could be anything. The only thing that we've been forced so far is W2 had to be positive, and now W1 has to be positive too. Okay, how they're related to each other, it doesn't matter for the example right now. We could swap these two labels and it would still be true. What matters is we can still draw our T here, where it's 0 on the left-hand side and 1's on the right, and both of our 1's are on the right, so we're fine. Okay, so far so good. If we can get the last case, we're good. Okay, so in this case, we're going to set both of our inputs to 1. We've got x1 equals 1, x2 equals 1. And now when we compute our weighted sum, again, still having the bias term, but we also have both W1 and W2 showing up. Okay, now this is where things get a bit tricky, is because now that we're in the 1-1 case of our XOR, we know that that should be a 0. We should output 0. So our neuron now must answer 0. For us to answer 0, our threshold must be greater than our weighted sum. And our weighted sum in this case is W0 plus W1 plus W2. So I've drawn it way out over here, because if this is W1 and this is W2, it's going to be way out there somewhere. So in this particular case, this is bigger than W0 and W1, or W0 plus W1 and W0 plus W2, obviously, because it's got both of those inside of it. It's bigger than both of them. And we were forced that W1 and W2 have to be positive by this previous line. We can't make them negative to try and do anything fancy here. So we can imagine now moving our line T. This tick over here needs to be 0. So to make it 0, we would have to move T all the way to the other side of it, which would make all of them 0. That's wrong. That would make these two wrong. This is still the best place for us to draw our T, but we're never going to answer correctly on this final term over here. So unfortunately, this means there is no way for us to draw a T that's going to divide these up. Okay. The problem that we're facing here is that these points that we want to divide, the zeros from the ones, are not what's called linearly separable. Linearly separable. And that means separated by a line, because that's what we're trying to do. We're trying to draw one line here, 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 something like that, and separate them between the zeros and the ones. But these particular points, the way we've drawn them, it's impossible to draw a line that separates the zeros from the ones without drawing a curvy, bendy line. That's not allowed. Okay, and that's what we mean by linearly separable. And so, in fact, this was an observation made of early neurons when they were first introduced quite early on, that they seem to lack a power here. They can't do XORs, but they can do ORs and ANDs. And this limitation, and a limitation it indeed is, was misinterpreted at the time as being a severe limitation, and maybe that neurons should just be abandoned. Why were we looking at these in the first place? And it took a couple decades before they were picked back up again in a serious way and reconsidered and realized this isn't such a big deal. And it's not such a big deal because what are we talking about here? We're talking about the simplest possible gates, or in this case, the simplest possible neuron that we might be able to build, right? And in in circuits, we take those simple gates and we put them together to make more complicated structures and more complicated circuits. That's the whole point. And our initial design with these neurons, why are we even talking about neurons in the first place? We're inspired by neural nets, which are a giant complex networks of neurons. We're going to put them together in a giant circuit, if you will, of neurons. And so we could compute, hopefully with one of those circuits, we might be able to compute whatever it is we're trying to compute, say XOR, even if we couldn't do it with a single neuron. Okay, so, and this is also one of the takeaways I want to take at this point, is that because we've been able to implement an AND gate, a NOT gate, and an OR gate, those are universal gates from a logic gate perspective, meaning that any circuit you could create with a circuit board, you can create with a neural net, at least using these kinds of simple artificial neurons. And so that means there's an equivalent power there. And that means we could effectively build a computer out of neurons, if we can build little neurons instead of the circuit boards that we create. And so for that reason, that means there's an immense power in neural networks if we can figure out how to code them and program them up and make them work the way that we want. We don't really want to just use them as logic gates like we're doing here, because we already have logic gates and we can do those already fine. We don't need neurons to do that. So the next question might be, what else can we use these for? And that's sort of the next purpose. Now, I'm going to end this video here, but in the next video, we're going to explore how we can actually build an XOR neural network, a very simple 5-neuron network or 3-neuron network, depending on how you're counting your neurons. And again, it's just a very simple network. We're going to show how we can build some to solve the XOR gate, and then I'm going to also show how we can evolve some neural networks to solve the XOR problem. So thanks a lot for watching, and I hope I see you in that next video.